Okay, so we are done with RC curve. Let's move on to the other stuff that we have to do in the script. So let's do something about holdout or some other methods that we talked about in the class, like stratified sampling, how to implement that. So we have already implemented a one way of holdout sample, which is to use sample function, take say 90% of the data, use that as a training, remainder 10% going to become your test. But there are a few more other ways of doing that. So one of the ways of doing that is through this function called runif. So all I'm doing over here is I'm creating a, a vector with 1,000 numbers, and these are continuous numbers, and they're 1,000 in total, and they're a random uniform distribution. So the first part over here generates those random numbers, which are in total 1,000. The outer function is order functions, which order these random numbers from 1 to whatever, 1,000. And those orders will be over here. So let's run this, and you'll see that if I do random IDs over here, you'll have 1,000 numbers which are randomly distributed. So the way it works is, I've already explained that, but let's see how it works piece by piece. So let's look at random numbers. So this is nothing but the output of a random uniform distribution of 1,000. So there are 1,000 numbers in here. They're continuous variables. They have uniform distribution. So that is good. But what order does is order gives. So for example, for this, if all these 1,000 numbers are arranged from lowest to the maximum, what will be the position of this number in that order? So that is what order function does. So if you do order on this, you'll get a random integers, which are nothing but the position of each of those random numbers based on their value. So I get 196 first and 523, 357. The whole point is that through this, I get random numbers from 1 to 1,000, a total in 1,000. So they're randomly ordered. So far so good. Now what I do is I use those random IDs to get corresponding rows from my credit data frame. So here I go to my credit data frame and I say, okay, out of random IDs, give me 1 to 500 rows and all the columns, and put this into a variable called credit underscore train. So once I do that, I got 500 rows in there. If I want to check, I can do this credit underscore train, and I got 500 rows in there. Similarly, I can put about 250 in my validation data set. So that's what I'm doing. It's a validation data frame. I go to my credit data frame and I take all the rows which are in the range of 501 to 750 in my random ID vector that I created in a previous step, and all the columns. So now 250 rows are in the validate, and then for the test I can do the same thing. Whatever is remainder I can put in here. So give me all the rows which are between 751 to 1000 in random ID vector out of credit data frame, and put that into a variable called credit underscore test, which is again also data frame. So this is another way in which you can have holdout data sampling. But we have already seen another version which is like using sample, and I give you another version of that where you do not have to worry about these numbers. You do not have to input these numbers. You can just take n row, which will give you the number of rows in the credit data set, and or any data set, and you can just plug numbers against that number, as we did with our example, 90% against whatever comes out of n row of credit. Okay, so far so good. Let's use a caret function to create something that we discussed in the class called stratified sampling. So for that, we'll use a function called create data partition. And let me go through this function, what it's doing. So create data partition is the name of the function. Be cognizant of the fact that it has mixed cases. So data has capital and partition has P capital. And it goes after the target variable. Because if you remember, the principal stratified sampling is that in both test and training data set, we will have the same proportion of our target variables. So here we define, okay, which one is your target variable, and that is default. And we need 75% of that in this training data set. And this is not a training data set, but it's a row number. So we'll look into what goes into this in train. It's just the numbers. And we want list to be false. It's not going to be the list. So now look in dot train what is in there. It just got a bunch of numbers. Okay, so these are the numbers which are between 1 and 1000, but in total they are 750 because we need 75%, and this is not a list. So if you do class on in train, it's a matrix, it's not a list. So we want it to be matrix, not a list. Okay, so and that is what this list is equal to false means. Okay, so let's go to the next step, which is to create a training data set based on these row numbers. So this is what we do. This is CRED is the data frame that has all the data in there. In train is all the number of rows that we are interested in to. Those 750 rows, 75% of the data, all the columns in there. Boom, it's done. And similarly, I can do minus over here, and I'll get the test created this way. Okay, so this way I got test and credit. We can look at the number of rows which are in there, and 750, 250. So 250 in credit and in the test, and 750 in the train. So this is another way in which you can have stratified sampling. So previous one is the example of the holdout. This is an example of the stratified sampling if you are interested in that. Okay, so now let's do cross-validation, which is really important. So for that, we use a function called create folds. So this is a function. Again, create folds will ask for which is your target variable, because you do not want to be in a situation where only one fold has all the defaults and other 9 folds have nothing in there. And then how many folds you want to create. So k is equal to 10 implies there are 10 folds. So we do that. Now, if you want to look at the structure of folds, it is a list. It has 10 elements in there. So this is how this output going to be a list. Be cognizant of the fact. Okay. Now, how we can create test and training out of that. So here I say, okay, out of my credit data frame, give me all the rows which are into the element of list called fold one. So this dollar says, okay, folds is a name the list over here. Dollar fold one is the element, so this is the element. This is the first element I'm referring over here. So give me all the rows which are in this element, which gonna be like 100 rows. So that will be my test. Give enter. So 100 rows have gone into test, and whatever that is not there in this fold 0 1, put that into test into train. So that will be my training data set. So that is my training data set. So as simple as that. And now I can do whatever I want to do with my test training. So that is fine. However, if I'm doing cross-validation, I have to run this whole process 10 times. So one option is I could do this script, this step 10 times, or I can automate that. So for automating this, there's a way I do it, and let's put this way over here. It's by creating a kind of function or script. And let me go through this code, exactly what it's doing. So here I use RLAB05. So if you remember, folds is a list. RLAB05, what it does is it apply a function to each element of the list. So there are 10 elements of the list. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 elements on the list. It will apply this function to each of these elements. And what function will it apply? So we define a function over here. So this function takes x, which will be folder 1 or folder 2 or folder 3 or folder 4, and then it will assign whatever that is not there in that fold. So if it's folder 1 the first time, so minus folder 1 will be their training, folder 1 will be your test, exact the step that we did in the previous commands. And thereafter it will calculate. Here I'm calculating C500, that is a decision tree function, I'll create a decision tree model where default is my target variable. And this tilde says that, okay, default is your target variable, and whatever remaining after default is your predictor. So default is my target, and all the 16 columns in my credit data frame after default, those will be my predictor. So this dot means all those columns except the target column. Comma, I have to give the data on which I have to create the model, and so the data is equal to credit underscore train that we created in the previous step. Okay, so over here that we created. So that is my data. And then based on this data, I'm gonna create this credit underscore prediction using that predict function that we use in decision tree. And then I'll create a variable called credit underscore actual, which will have the actual defaults. So those will be over here. And then I'll calculate the kappa2 statistics over here, kappa2 function from IRR package. And then I will supply the actual credit defaults and the predicted defaults. And I'm only interested in the total value. So that's the reason why I wanted that IRR package to be there. And then I'll return the kappa. So this CV underscore result at the end of this will have 10 kappas in there. So let me hit enter. And so it could not find a function 5.0 because I have installed the package called C540. So let me do that. And this is the same package that we dealt in decision tree. So this has nothing to do with naive Bayesian classifier, but here I'm talking about the holdout methods, the stratified sampling, the cross validation that we talked about in the class. And let me call the function C50. Okay, so library has been loaded, all the functions are there. And now let me run the same script that we had previously, and now it should all go fine. So everything has gone fine. Let me see what is there. Let me look at the structure of CV underscore results. And it's a list with 10 values in there. So the first kappa is 338, 209, 36, and we'll take a mean of all these values. And that mean would be a average predictor of how good our model is. So we have already done this. Let's calculate the mean. And for mean, what we have to do is we have to unlist this this output. So we have to convert. If we do a mean on the list, it's not going to do anything. So we unlist it first, and then we calculate the mean. And this is a mean of our model, 29.09%. So that is the kappa. Okay, so that is there. Now, one more thing that we have to do is how we can improve the performance of our model. So here our model is C5.0. It could be naive Bayesian model. It could be support vector machine that we're going to talk about next week. How to improve that. And Caret gives us a very good function called train. And train goes through all the permutation combinations of the tuning parameters and generates a best model that is possible. So you do not have to do all the hard work. So let's see how that works. So here I'll call train is the name of the function. Default is a predictor, and then dot over here says all the columns in the data that you're working on, which are not default, which are predictors. That's what this dot represents. And the data would be credit underscore train. The model or the algorithm that I want to apply in this case is C5.0. So that is decision tree. So now once I hit it, it will run for a while because R is doing a lot of heavy lifting. It's going through all the permutation combinations of parameters, all kind of things it could do to find out the best optimal model for you. So give it some time. So as you can see, this red button over here, it's all red, and that is because it's doing some work. And once we have this model built, then we'll do the same thing that we have done a million times. We'll create the prediction based on this model, and we'll see how good this model is. Still working. Still working. So you can see like CPU utilization is high. The good thing is the memory utilization is not that high. So that is fine. So it's doing some heavy lifting over there. Okay, so it seems like the model is done. And now we have to go to the next step, which is to create the prediction. So let's create the prediction based on this model, which will be in variable P. The syntax remains the same. Predict, M is the name of the model, and credit underscore test is the data frame, which has our test data set. Okay, and now let's just do table. We can also go with cross tab through Gmodel if you wish, but here let's keep it concise, and we can see like, okay, um, out of um, out of so how many rows were there in our test? So credit underscore test, 250 rows, 28 and 44 are bad. So 28 plus 44, so that's about 28.8% accuracy rate. And the reason for that is because with this splitting that we did, we only have 750 elements or rows in our training data set. Had we had like 900 rows, this thing will improve. So, so this is another way in which you can improve the performance by going after, this train function will pick up the most optimal model for you. Okay, so far so good. Now another thing that you can do is you can look at the prediction in terms of type to be raw in this case, and it will give you yes, no, no, yes. You can also go after in terms of probabilities, and it will give you yes and no. So you can look at how well your model is doing through putting type to be raw and type to be probability, and you'll get different outputs. Okay, so far so good. Another thing that we can do is we can specify some training control parameters or tuning parameters, and I'll show you an example of that. So first thing that we do is we define some tuning parameters, and that is through a function called train control. So train control is a function. It asks for, okay, what kind of method for sampling you're going to be using. So I put CV over here, that is for cross validation. And then I can also put, say, um, boot, B-O-O-T, boot, that is for bootstrapping. If you remember from our class discussion, bootstrapping, so it will do bootstrapping. The number of cross validation I want to do is 10. And then selection function, which particular model I want to select out of those 10, I put 1SE. So 1SE is a function, selection function, where I pick up, say, for example, fourth model is the best one. And then I look for all the models which are within one standard error of that best model. And out of them, I pick up the simplest of all model. Because if I take the most complex model, even though it's performing great, it will have problem of overfitting. But if I take a model which is not that far away from the best model, but it's kind of simpler, that problem could be alleviated to some extent. So that is what 1SE function is. And so control has all these control things in there. So once I put this information in my model generation, um, um, in training of the model, then it will use cross validation. It will use tenfold cross validation, and will use selection function 1SC to select the most optimal model. Along with that, I can also put a lot of other tuning parameters through an optional thing called expand.grid function. And let me just walk you through what expand.grid function does. So here, again, what I'm doing is instead of writing everything in one big function, I'm chunking it out in different parameters. And so control is one parameter, grid is another parameter, and it has all those values inside them. So here I'm saying that my model will want to be a decision tree. I will use boosting. So for the first iteration, I'm going to use 1 iteration of boosting. The second I'm going to use 5, the third one 10, the fourth one 15 iterations, 20, 25, 30, 35. And winnowing will be false. So winnowing is something that I didn't talk in the class. What winnowing means is in decision tree, if you remember, we get the importance of the variables. So in winnowing, the algorithm just picks up those variables which are important and throws away those variables which are not important. So do you want that to happen? Just work with those variables which are important, throw away those variables which are not important. If you choose winnowing to be false, it will use all the variables, or you can choose winnowing to be true. So in this case, I choose it to be false. Okay, so if you want to look at your grid, just call this grid, which is nothing but a variable, which has all these information in there. So it will run 8 iterations. It will have it will have a model to be 3. The trial would be 1, and the winnowing would be false. Then the trial would be 5. That means boosting iteration is going to be 5. Boosting iteration is going to be 10. Boosting iteration is going to be 15, 20, 25, 30, 35. Okay, so with that, now I call my train function, and let me just walk you through what it's doing. So default is a target variable. Whatever that is not default, those gonna be predicted. That's what dot means. Our data gonna be credit underscore train, which is nothing but 750 rows that we selected in the previous method. The method algorithm that we're gonna be using is C5.0 decision tree. The matrix on which we're gonna say, okay, this particular model is great and this particular model is not so great is kappa statistics. So that is kappa. Our training control would be the control that we created over here. So it will do 10-fold cross validations. And then along with that, we're gonna do 8 iterations of the same thing with different boosting iterations inside. So the first iteration will have only 1 boosting, and that will use cross validation 10 times. The second one will do 5 boosting iterations in that algorithm C5.0. And then the third one will